Welcome to the lecture on melting and casting of cast metals. So, in this lecture we will have the introduction about iron casting and we will typically discuss about the cast iron. So, we will discuss about different varieties of cast iron, we will discuss about the metallurgical aspects of solidification in case of cast iron and other issues. So, cast iron, what is the importance and why it is in demand? So, cast iron is basically in terms of foundry casting, the amount of cast iron components or the weight of cast iron components which is produced is basically 2 times than all the other castings. So, this way we can understand the importance of iron castings or cast iron castings. So, normally when we talk about iron castings we refer to the cast iron because this cast iron has been used for many hundreds and thousands of years and it has been in importance because of many of the advantageous properties, the properties which has edge over other kind of materials, like it has a very good castability, it has good combinations of machinability, strength, hardness, corrosion resistance, all that. So, it has, because of these properties and because of the ease with which it can be cast, this material is basically giving so much of importance, and most of the components, if you talk about the iron carbon system and if you talk about the alloy of iron carbon base, then because of certain advantages associated, like in terms of casting, you always prefer to have the use of cast iron. So, what is cast iron basically? Cast iron is the alloy of iron and carbon where carbon percentage is more than 2%, and apart from carbon you have other alloying elements like silicon, manganese and small amount of sulfur and phosphorus. So, that is cast iron. Now, if we try to see what is that difference in case of cast iron and steel. So, when we talk about the steel, if we see the iron carbon diagram at this point, it goes like this, and here. So, this way it goes, and this is a normal iron carbon diagram. You have equilibrium as well as metastable equilibrium diagram. So, in this axis you have percentage carbon and this is the axis of temperature. So, what we see is this is close to 1535 or 1539 degrees C, and then this is 723 degree centigrade line, this is 1135 degree centigrade line. So, what we see is that as the carbon percentage is increased, the pure carbon with the pure iron. So, this is 100% iron, and in this direction you have the percentage of carbon increasing. What we see is when there is pure iron, it melts at about 1539 degree centigrade, but as the carbon percentage is increasing, this liquidous line basically decreases, and this point is known as eutectic point, and here the carbon percentage is 4.3% and this is 2% and this is the eutectoid point, this is 0.8%. Now, what we see is the pure iron which melts at about 1539 degree centigrade, once we alloy it with carbon, then this melting point at this point again it is at a single point. So, it is like a melting or solidification of metals or pure metals. So, this is known as eutectic point. So, this is the getting finished, this is the solidification is here at this point, temperature of 1135 degree centigrade or 37 degree centigrade. So, the castability basically is improved in the sense of the temperature, your temperature requirement for melting is less. So, even cupola, that is why is enough to produce the grey cast iron or cast iron varieties of materials. However, if we talk about the steel, steel is normally the iron carbon alloy with some alloying elements, but then it is before this 2% or 1.5%, and if you take this range, this is quite high the temperature. So, in that case you require a furnace where you have to produce, where you have to melt the material, and furnace should be able to generate high temperature. So, in that case the furnace requirement has to be different, the lining requirement has to be different. Apart from that, what happens in the case of this cast iron, apart from iron and carbon, one of the chief alloying element which plays an important role is the silicon. So, what happens? The silicon is a graphitizer. So, basically the carbon which is there in the steel up to this point, this carbon is normally present as in the form of combined form or with iron as Fe3C. So, because this 6.67% is the Fe3C, this is your intermetallic compound cementite. Now, what happens in the case of cast iron, the composition as well as the cooling is adjusted in such a manner that when it cools, this excess of carbon is basically changed to graphite. So, that is free carbon. So, in that case this carbon is not in the form of Fe3C. Now, it depends upon the cooling rate and composition. The carbon may transform to the combined state, that is Fe3C form, or carbon may go as the graphite. Now, this process is known as graphitization. So, graphitization means the carbon which is there in excess, that basically has to change to the graphite form. Now, let us see what happens if suppose you have this point which is coming, we are melting at this point. Now, at this point when you come at this point when temperature has become less than this is a liquidus line. So, once you come below this liquidus line, then you have liquid plus austenite. So, what happens? This is your austenite, this is austenite plus liquid. So, this is your cementite, and then this is your basically eutectic line. So, that is ledaburite. Now, what happens once you have come to a temperature below this, you have at this point austenite plus liquid. So, you have austenite, solid crystals of austenite coming out, and this austenite has a composition corresponding to this point. So, as the temperature will come down, this austenite will basically be losing the carbon. So, at this point certainly this is a 2% of, so up to this point when it comes, the austenite has maximum of 2% of carbon. Now, after this, so once it comes just below this line, the freezing is completely complete, and at this point you have austenite of maximum, this has composition of 2%, but once it comes down, again the carbon solubility in austenite decreases as per this line. So, once it comes to this line and touches this line, at this line when it comes, the austenite which was there, it will be losing the carbon, and maximum it can have 0.8% of carbon. So, it will be somewhere close to 0.6 to 0.8% of carbon it can maximum dissolve. So, all the carbon which is there extra, all these carbons will be disposed of, it will be left by this austenite. Now, this carbon once it goes, it may appear either as combined form or as a graphite form. Now, the chief role of this alloying element silicon is that silicon is a graphitizer. So, what happens because of the presence of silicon and also because of the low cooling rate, this carbon is basically present as the graphite. So, graphite is soft, and that is why in the cast iron, as you cast in normal circumstances, if you have enough of silicon and cooling rate is moderate, you get the carbon in graphite form. So, that is how this, and once it further comes down, then depending upon the graphitization extent, this once we know that once we come after this line, you have this composition, this is your eutectroid. So, you have this perlitic structure, you have ferrite plus perlite. So, the matrix may be ferrite or perlite or combined of ferrite and perlite. Now, again what type of matrix you will get, that depends upon the extent of graphitization. So, the graphitization is maximum, then you are likely to get the ferritic type of matrix, because most of the carbon which is released, this carbon is present in the form of graphite because of the graphitization process and because of the presence of alloying elements like silicon. So, in that case, when the graphitization is maximum or it is high, rate of graphitization is better, in that case you get a ferritic matrix, and if that graphitization is not so high, then or that may be because of not adequate amount of silicon present or maybe because of slightly larger cooling rate. In that case, what happens that you may get a perlitic type of matrix. So, basically the silicon is working as a principal alloying element which controls the microstructure of these cast iron components. So, what we see, we can look at this figure which tells that now there are varieties of cast iron as I told, and as we see in the case of steels, the percentage here is silicon percentage is maximum 2, but in the cast iron it goes up to 3 or 4 even, and what we see is when the silicon percentage is more, we see that this is grey cast iron. So, grey cast iron, when silicon is more, there will be more graphitization and carbon will be separated as graphite structure. So, that is why you get grey cast iron, whereas when the silicon is less, you get the white cast iron. If the carbon percentage is more than 2, up to carbon 2%, you have the variety of steels. However, if the carbon percentage will be more than 2 and silicon percentage is also less, in that case what we see is you have the variety of cast iron that is known as white iron, and white iron basically depending upon the heat treatment given to it is converting to malleable iron, that we will discuss later. What we see is when the cast iron has larger percentage of carbon as well as silicon, in that case more graphitization takes place, and because of that this grey cast iron is formed, where this cast iron is basically defined in because the fractured surface appears grey. So, in that case this grey cast iron has a fractured grey surface and it has a flaky type of graphite. Then this nodular cast iron, again it has a larger percentage of carbon as well as silicon. So, here also the carbon has to be there, but in the nodular cast iron basically the requirement is that it should have very less amount of sulfur, because the sulfur interferes in the nodularization process. This diagram further tells that how you get the different varieties of cast iron. what we see is when the silicon is higher and carbon is higher, you get the gray iron, and when you have these smaller quantities you get the white iron, and in between you get the mottled iron. And if the cooling rate is maintained as low value, in that case this curve will shift towards left. So, if the cooling rate is lower, then even at the smaller values of silicon and even carbon, you may get the gray iron structure. So, and if the cooling rate is fast, then this curve will move towards right, means for the same composition you are likely to get even the gray iron structure or white iron structure depending upon the cooling rate. If the cooling rate is less, it is likely that you will get gray iron structure, or if not, then you may get the white iron structure if there is that composition for a particular composition. Now, what we see is you have to understand the mechanism of solidification that we have anyway discussed, that how this solidification is taking place when we go below this temperature, how this carbon, excess of the carbon will be coming out of the solution, and then this austenite will also lose the carbon, and then finally as it loses, depending upon the conditions, depending upon the cooling conditions and also the presence of alloying element, this carbon will either be in the form of graphite or in the form of Fe3C. So, this way at the room temperature you may have different matrix, maybe pearlitic, ferritic, and you may have the carbon in different forms. So, what we see is we have to discuss about the types of cast iron. So, what we see is in the types of cast iron, first variety is grey cast iron. So, grey cast iron is defined as that variety of cast iron where the carbon is present in the form of graphite flakes. The fractured surface appears grey, that is why it is known as grey cast iron. Now, in the grey cast iron, what we have seen is that the value of carbon as well as silicon has to be on the higher side, and also the cooling rate has to be moderate. So, in that case the grey cast iron is formed, and in the grey cast iron basically your flakes are like this. So, these are the flakes. So, these are the graphite flakes which have the pointed ends, and this is basically giving the material some inferior properties when they are subjected to tension. But this graphite grey cast iron has other very good properties. So, like good machinability, good damping capacity. So, that is why grey cast iron is very much favored for such typical applications like machine beds, and many components are made by grey cast iron. Next variety is white cast iron. So, in the white cast iron the carbon is in combined form, that is Fe3C. Now, when this white cast iron is formed, the white cast iron is formed when the amount of carbon and silicon both are less on the lesser side. So, basically carbon as well as silicon both are graphitizers. So, basically carbon and silicon both are graphitizer. So, in this case when the carbon and silicon both are on the higher side, then when the carbon separates out, since it has a graphitizing tendency, then your carbon is going in as the graphite flakes. But in this case when the carbon is less and silicon is also less, and if the cooling rate is little fast, in that case this carbon is in the form of Fe3C. So, that is in the form of carbide, and that is why this is known as white cast iron, and the name white appears because the fractured surface appears white. So, it has very high hardness, ductility is less, and it is not at all, mostly it is not used for any engineering purposes, except that where very high compressive strength is desired, like for rollers in steel plants. So, what happens, there is a variety of cast iron, that is malleable cast iron. So, this is basically you are getting from white cast iron. So, from white cast iron, since it is of no use, we do the heat treatment, in that we are heating that and holding this white cast iron at a temperature of, I mean, more than the transformation temperature, and at that temperature we are holding for a very large time. So, in that case what happens, due to holding for a large amount of time, this basically decomposes, and this is decomposed to iron plus carbon. So, this carbon is released as free carbon or temper carbon. So, in that carbon is in temper form. So, temper or free form, this carbon is so small nodules, in that case you have smaller nodule type of structures of free carbon is present, and it basically gives a large amount of ductility and malleability to the component. So, this malleable cast iron, although this heat treatment cycle is quite large, but this material is used for many automobile components where you need the malleability of the property of ductility. The next variety is ductile iron. So, ductile iron is that variety of the cast iron where carbon is in nodular form. So, what happens, ductile iron, now in this case you get these small nodules or small free carbon, small sizes of nodules, but in the as cast form we can get the nodules of the graphite by doing the treatment of this cast iron. So, for the same composition of cast iron towards the higher side of carbon and silicon, if we treat the melt with magnesium or cerium or yttrium, then what happens, you get a cast iron which has larger shape of nodules. So, these graphite nodules, because of the presence of these graphite nodules, it is known as nodular iron, or even it is also known as SG iron, spheroidal graphite iron. So, it has a very good combination of properties. Because of these nodular shapes of graphite, the adverse effect which we get in the grey cast iron because of the pointed ends, that is gone, and so its property is quite better. So, we can get it by the magnesium treatment. There are many ways of doing the treatment of this magnesium in the case of this ductile iron, and we get a good properties of ductile iron. So, then there are other varieties also like mottled iron. So, what happens that for a particular composition and depending upon the prevailing cooling condition, what happens, some part appear as white and some part as grey cast iron. In that case they are known as mottled iron. So, as we have seen, so that you have different sections, some part as white and some part as grey. So, that is known as mottled iron. You have also chilled cast iron. So, because of the chilling effect, some part is white cast iron and some part is grey cast iron. So, where the chilling is not there. So, you have this way, but mainly you have these 4 varieties of cast iron. Now, microstructure. If we talk about the microstructure in case of cast iron, you have mainly the microstructure consisting of few phases. and these phases are outlined there. So, what we see is the phases are like graphite. So, carbon is in the form of graphite. Carbon may also appear as cementite. So, basically what we see is when carbon is in the form of graphite, it induces the ductility or malleability to that variety of cast iron, whereas if there is carbon in the form of cementite, in that case it induces the hardness or brittleness to that particular variety of cast iron. Ferrite is the phase, as we have understood so far, that depending upon the extent of graphitization, you may have a ferritic matrix or you may have a pearlitic matrix, and or else you may have the combination of these two. Steadite is a phase which is nothing but it is a eutectic of iron and phosphorus. So, somewhere close to 1000 degree or so. So, it has a very lower melting point, eutectic is formed. So, some of this is used and beneficial, and it imparts better fluidity to this cast iron. So, that is why for when we are going to have the cast iron component being cast in shallow sections or thin sections, in that case some amount of phosphorus if it is present, because of this eutectic formation, low melting point eutectic formation, that may help us to give us a large amount of fluidity. Austenite, as we know, austenite is otherwise not a stable phase at room temperature, but then if we add nickel as the alloying element, chief alloying element to a larger extent, then nickel being the austenite stabilizer, you also get the austenitic phase in that cast iron. So, depending upon the conditions, you may have the formation of these different phases, you may have different kinds of matrices, and you may get different varieties of cast iron. They are, that is grey, mottled, white, malleable or ductile iron. So, in the coming lectures we will discuss about the practices of melting for these different varieties of cast iron and what are their characteristics, what are their uses, how to see. So, there is one more terminology like carbon equivalent. So, all these things we can discuss in our coming lectures. Thank you.